Together, we are rapidly deploying solutions for warfighting communications that speed the exchange of information and shorten decision-making channels. We are building resilient mission architectures to mitigate threats and ensure dominance throughout space. And with our capabilities for space domain awareness, we help ensure the safety, security, and sustainability of our nation's activities in an increasingly contested environment. In the face of the unknown, we stand ready to serve the brave men and women who act as our guardians and using cutting-edge technology for protecting our future. Together, we defend above.
Hello, welcome everyone. I'm Deborah Werner, Space News Silicon Valley correspondent, and I'm delighted to be here today with a panel of experts to discuss very low Earth orbit and its applications for national security. I think I'll let each of the panelists introduce themselves.
Thank you. Thank you, Deborah. Dean Bellamy, Executive Vice President for National Security Space at Redwire, former retired Air Force Colonel, almost did 27 years. So excited to be here and with my distinguished colleagues on the panel. Thank you, Deborah.
Thanks. This is Jason Wallace. I'm President of Government Programs at Phase 4. Phase 4 is an in-space propulsion company from Hawthorne, California. We were founded in 2015 specifically to address the needs of propulsion from the growing satellite industry, as well as advance our radio frequency thruster, specifically to focus on non-traditional propellants, specifically air and other unique propellants, such as chemical propellants, hydrogen and green propellants, focused on delivering to the warfighter and to the various orbital domains from VLEO to cislunar and deep space.
I'm Seth Lacey. I'm the Space Mobility and Precision Maneuver in the Air Force Research Laboratory. I've been there 22 years and I'm excited to be here with the rest of my panels.
Good morning, I'm Jeff Shirk with the Aerospace Corporation. I've been in this industry for 35 years, 24 of that in the Air Force, primarily in space operations, space surveillance, space control, missile defense, hypersonics, directed energy, and a few other things. So happy to be here. Thanks, Dean, for inviting.
So I'd like to start by asking Dean, what is VLEO? When I wrote about this in 2021, people told me it was 250 to 450 kilometers, generally below the space station. But what would you say?
Hi, thanks, Deborah. That's a great question. So actually, I believe we'll get a lot of disagreement in here. Is VLEO below 450? Is it below 300? And I would say that's the reason we're really looking between the area between where air ends and kind of space is in that area. And I think this is really a pathfinding journey. It's the new frontier. So if you think of the frontiers we've looked at in the past, I think this is that next frontier. So I think that as we're on this journey, we will actually optimize where you operate. Is it 325? Is it 410? We'll find out based on the atomic oxygen and other drag and other, really, I would say, capabilities we're going to face. But I think it's open for discussion, but that's why we're charting this new path and this new frontier.
Yeah, I think it's an interesting question because it's difficult to define a region right now when we're still learning a lot about the environment above where traditional lifting surfaces operate. And so maybe it's an academic response, but it's basically the regime where lifting surfaces no longer support and where you can actually achieve orbital velocities. And so you're actually orbiting around the Earth. And there's a lot of technologies that will open up that regime. And that's where a lot of the programs, a lot of the developments that are happening right now are going to help define what that region is.
I don't know if I'm going to have a great answer to that. So you think about in the higher end, you're looking at particle flow or mean free path is really far, and you're not, continuum dynamics is not really what's happening. And then at the lower end, as you get closer to the surface of the Earth, you're going to see dynamics that look more and more like traditional fluid flow, and but those are pretty gray areas on both ends. So I think we will learn and explore together.
Yeah, I guess what I would add to this is the potential of transitioning between different altitudes and what those different altitudes can bring to the table from a national security perspective. So very interested to see this technology advance.
So Jeff, will you expand on that and what the altitudes could offer for national security?
So flying in VLEO, you're closer to the ground and you can certainly achieve higher resolution imagery, higher accuracy, signals intelligence. By being in the atmosphere, your orbit is less predictable, so you can start to think about things like unmanned reconnaissance. It's also harder to track and target satellites in VLEO because of that uncertainty in the orbit. Being able to take advantage of the aerodynamic environment and being able to exploit that so that you can maneuver in track and cross track presents a lot of really good opportunities for reconnaissance and survivability and constellation management.
Did anybody want to add anything to that?
I would just add for resiliency, right, if you look at having a hybrid architecture or orbit diversity, provides you what we learned really, if you go back to the space shuttle, right, 1986, right, if you have all your eggs in one basket, right, you could lose capability. So in case something inadvertently happened in one of the other orbits, an inadvertent debris issue that unfortunately might have hindered our ability to get some capability from LEO, maybe communications, having an augmentation capability or orbit diversity allows you to be more resilient.
Got it. So one of the challenges, the obvious challenge here, or one of many perhaps, is propulsion. So we know that once you get to orbit, you have the advantage of remaining in somewhat of a stable orbit, but you're losing that advantage here. So how do you address that, Jason?
Yeah, there's a couple different ways to look at it. I mean, in the VLEO environment, you're encountering the low density atmosphere that exists up there, and so your spacecraft experiences drag. And so in order to maintain your orbital altitude and maintain operations, you have to compensate for that. And so propulsion is a critical component of maintaining your orbital velocity in those regimes. A lot of the promise of VLEO is not just providing the drag compensation, but also collecting the propellant in situ while you're actually in orbit, which is particularly important. The lower you go, the more drag compensation you have to provide. And that just means you have to either carry a lot more propellant on board, which removes payload volume and makes it much more challenging to design your spacecraft. Or, like I said, the promise is to be able to collect that propellant in situ and actually, essentially operate limitlessly.
So Deborah, if everybody can hear me, I'll throw this out to maybe I can, the other panelists to kind of make this a kind of fun discussion. But I think we're standing on the shoulders of test pilots like Chuck Yeager and all the folks that, we said we couldn't go Mach 1, right? We couldn't go this altitude. And whether it was propulsion or another technology, could we do that? And, they spent years and, a lot of them lost their lives as they were, expanding that new frontier for what we have today in air power. And I think that in the same token, we're kind of starting that new frontier here. What do you think? I'll pass it to the other ones.
So I think we're pretty excited to learn more about this regime. We have a lot of unknowns in this new regime. Yes, we passed through it on the way up, then we passed through it when we're deorbiting. We don't really live in this area, and the challenge of collecting your fuel as you fly, there are a lot of exciting unknowns for us to go and explore, and that's, I think, where, from a research lab perspective, that's our gig. We're pretty excited about that.
And I think VLEO offers a lot of new mission concepts that most of us haven't even thought about yet, because we haven't really operated in this environment, but if you consider some of the advantages of VLEO and what you can do with maneuver and being closer to the ground, modifying your constellation to achieve different objectives, I think offers a lot of opportunities that we'll be exploring in the future.
I think the connection to the test pilot concept and experimental aircraft is actually pretty apt, because I don't think the satellites that are going to be designed for this regime are going to look like traditional satellites. I mean, SabreSat is a great example of it. It looks very different. And so I think that's a pretty apt analogy there.
Will you tell us a little bit about SabreSat and both of your programs to explore VLEO?
Yeah, absolutely. At Redwire, we're really proud to actually have two satellites, SabreSat here in the U.S., and then we actually have PhantomSat. And one, I'll call on you, raise your hand in the back. Juan and his team over in Belgium are leading SabreSat. And yeah, we're really excited. We think this is really a leap ahead technology in an area and frontier for national security, space, civil, and you think of the scientific and atmospheric research for civil, whether it be NOAA and NASA. We see that there's a lot of applications here, and we actually are excited on both of the satellites. Our teams, we have two great teams that are leading the effort, looking at the different components, aerodynamics, and those types of things that they need. But really proud of the effort and really excited to see what the future holds for both programs, the one in Belgium and also the one here, SabreSat US.
And so Phase 4 and Redwire have DARPA contracts to explore VLEO. What can you two tell us about those?
So, just at a high level, the concept behind the DARPA Otter program is to explore an air-breathing satellite system. And so, the two companies, Phase 4 is focused on the air-breathing propulsion side of things, as talked about before, the concept of actually collecting that propellant in situ, and then obviously pairing that with the ability to operate in that regime, and that's where Redwire comes in.
Yeah, I would just say, we do, I would refer to our Marcom team. They can give you more details for sure. But, we're excited to build a spacecraft, and we're excited to partner. Not only do we partner with DARPA, we're partnering with AFRL, we're partnering with other folks in the Space Force, we're partnering with NASA. We're excited to have a chance to work with our customers, whether they be government or commercial, to really kind of advance the state of the art, right? And in this area, I think we really are pushing the state of the art, and we're doing it in a way that we believe is excellence in execution, right? We're really pushing that, as well as we're pushing knowing, right, that this is a new frontier, right? And we're going to learn as we go and as we're building these. And that's the exciting part for our engineers and I think our customers. And as we're going to be learning and exploring this new area, no different than I think if you go back to the 60s when we said, hey, we're going to go to the moon and explore that. I think it's the same type of spirit we're seeing with our internal workforce and our partners that we work with, as well as our customers.
What kind of technologies need to come together to make VLEO work?
I guess I'll take a shot. Since you're flying in VLEO, you're going to have a lot of drag resistance, and so you want to have a high ballistic coefficient spacecraft design. That's something that we don't do today. We try to make our satellites light so that we can launch more of them at a cheaper cost. But to stay in VLEO, you want to have a high ballistic coefficient spacecraft design, perhaps a design that can manipulate the aerodynamic forces and actually, promote lift and maneuver. You probably, since your passes over your tracking telemetry and commanding sites is going to be shorter, you're going to want to probably work with edge processing to do your signals or imaging processing on board, so that when you downlink, you can do that, quicker. those are a couple of the technologies that I'm thinking about, and I'm sure there's a few more.
So it's a new regime, and we have a lot of things to learn. I think there's a materials science thing. We've done a lot of materials in the space environment. On the space station, you see a lot of atomic oxygen, but that's going to be enhanced in this regime. So we have a lot of understanding to do on the material science side. I think the physics of the environment is something we're going to improve a lot. Our understanding in the next few years as we get through some testing, understanding the behavior of the environment and what drives that behavior. I think we're going to learn a lot and improve our prediction capabilities a lot.
Deborah, the interesting fact, Deborah, is I'm going to kind of pivot slightly. A lot of people ask me, VLEO, isn't that 5-10 years from now? Why now? Why is that possible? And I've got a lot of friends in the audience I've worked with in the past and worked for. And I would say, really, in my opinion, not only has power capabilities changed immensely over the decades, not only has payloads matured, right, and the cost has gone down, not only has propulsion capabilities changed, materials, exactly what Seth was saying, materials have changed, but compute power has changed, right? If you go back and look at the shuttle 28646 is what it flew on. All of everybody's iPhone today is like probably 20 times more powerful than that. And so I think we're really taking advantage of really where we see the optimal technologies are really right for us to tackle this new opportunity in VLEO.
And to add another perspective, the VLEO environment is a really tight control loop. I mean, the design of a system that can operate in a drag environment, kind of causes this systems engineering challenge where you need high efficiency power generation, you need high efficiency electric propulsion, and then you need that all to come together in a satellite that can be launched and can quickly get out of hand. But I think to the point about like why now, I think it's a lot about high efficiency solar arrays and also just an incredible growth in the development of electric propulsion, and it really comes down to high efficiency, high thrust to power, converting that solar power into thrust to do drag compensation. So it's a unique time, to have those two capabilities.
And I would just add one thing. Let's look at AI and autonomy, right? How far we've come. And I know, I know at Redwire we're really proud to be working on the AI and autonomy side with something called Caesar. If you're not familiar with that, please go see Altad Rose over there. But no, I really think that's a key thing too, right? Because you're going to have include state-of-the-art autonomy as well.
Yeah, it's a.
Oh, no, I was just going to add on to Dean there. With autonomy, that includes constellation management and ground control, because you can have a large constellation of satellites up there that are not staying up there for a long time. They're constantly changing their orbit, and so doing all the mission planning and the contacts with the ground, there's a lot of automation, and that kind of goes with the theme of the conference here this week.
Yeah, it strikes me it will take a ton of modeling and simulation to understand and make this work. Let's go into the applications some more. Why is VLEO important to ISR or important to communications?
I'll take a stab, and I'll let my colleagues look at it. I think it offers you the ability to do more rapid prototyping. Maybe you can take some lower tier technologies into rapid prototyping. Maybe you can move airborne platforms, for example, maybe an optic or an RF platform into that regime and do testing. So I think it offers the ability as kind of in the prototyping testing to do that, as well as I think it offers the ability to augment existing capabilities we have. So potentially to get more persistence. You're closer to the Earth, so you'll get, of course, the advantages of being closer to the Earth from an ISR perspective.
Yeah, one kind of interesting aspect of VLEO is that it's actually a self-cleaning orbit. We're seeing a large proliferation of satellites in LEO. It's getting crowded, certainly manageable, but one of the advantages of operating in a low orbital altitude is that once your mission is done, you're out of orbit, in minutes instead of days or months or even years.
concur with all those observations. I think another one to think about is launch, in that you can bring either smaller rockets to get the same payload into orbit, or you can put more payloads or larger payloads into work with the same rocket. So I think the launch side gets easier as well.
And I guess to go along with that theme, LEO is getting fairly crowded, and there's a lot of discussion and a lot of research about orbital debris, and I think they call it the Kessler effect. If you have one breakup, that increases your probability of having more breakups, and so LEO has the potential of becoming unusable. And if that is the case, which we all hope that is not ever the case, VLEO would offer an alternative to continue to provide space services while we try to figure out how to clean up the LEO environment.
Yeah, that would be very difficult. So people have touched on the resiliency piece, which I think is important to this discussion. Jason, you mentioned it's a self-cleaning orbit. And somebody else mentioned that it's difficult to track satellites. Was that Seth or Jeff? Yeah, difficult to track or target things in VLEO. Does anybody else have anything to say about the resiliency piece?
Yeah, I mean, most important on resiliency is mission assurance, right? None of us could ever expect a day without space, right? I remember when I was in uniform, and since we all talk about we couldn't do a day without space. I mean, how many people think, and then just show of audience in the hand, how many people use space today on the way here? You used your maps on your phone, right? You might have used cellular communications and other things. And really it's linked to our way of life, right? And not only in the US, but in the world. And so if you think, I was talking about this earlier, how many of us thought in the early 90s when we were doing GPS that John Deere, right, would be using GPS for planting crops and everything. And so if you can imagine a day without space, it would change the way we do banking, the way, I mean, gosh, how many of us pay at the pump, right? You would actually have to go in and actually pay, right? Actually at the gas station, like, that would seem like so old school, right? It'd be like my dad saying I walked uphill both way to school, right? But I think the resiliency aspect is just to make sure that we actually have space capability. Now, augmentation and what level we'll find out if it's communications. But I really see this as no different than 20 years ago, right? When Planet or some of these other smaller satellite companies said, hey, I'm going to go build a commercial EO satellite or Capella or Umbra and others. And I really think that ties into the spirit of this conference is, the fact is we have to have space, but it comes in different flavors and it looks different, right? It's not big, it could be big, could be a small satellite, could be a VLEO satellite, could be a MEO. I think that's the key. The diversity is the key.
Yeah, I think you mentioned a couple of the elements of the resiliency piece. I mean, Seth, I think you also brought up a good point that the VLEO environment being closer allows us to launch more capably, get assets into VLEO much easier on a wider spectrum of launch capabilities, and so I think it does open up the resiliency piece, being able to rapidly reconstitute or deploy new assets into orbital regime and not be limited by specific launch vehicles and orbital slots and all of that.
Thinking back on some of the automation things we talked about, and we build a lot of inexpensive spacecraft that are actually pretty reliable writ large, but individually a spacecraft can reboot or something can go wrong and can recover itself, and usually there's a human involved in getting it all the way back to functionality again. And that's going to be a different challenge in VLEO, where I think some of the AI ML technologies advanced incredibly in the last couple of years will help us build more automated spacecraft that can get back up and healthy after a reboot or something has gone wrong. They can take care of it. Being able to take care of yourself is much more important, I think, in VLEO than in some of the higher level versions.
So I guess being a former Air Force guy, I kind of think of resiliency and the capability to, should we ever have to go into combat, prepare constellations, with the right amount of services, comm, ISR, nav, to be able to service a particular area of operations. And I think VLEO has the potential there for rapid launch, rapid reconstitution, and focused attention on specific missions to support specific customers.
And Jeff, to that point, and I know Seth brought this up earlier, if you look at the cost of launch, right? What SpaceX has really been able to drive the market and the cost of launch, and companies like Firefly, right, have done just a tremendous job in this market too. And I think that they've opened the ability on the launch side of the house to support a VLEO capability at an affordable cost, right? So really hats off to the launch guys.
What would you say to somebody who asked when this is coming? Are we talking next year? Are we talking 5 years, 10 years to start seeing demonstrations?
I would say, at least on our side of the house, I would say both with Europe and also here in the U.S., we're working on it now, right? As far as launch dates, those are going to be driven by a number of factors, right? But really, I would say it's now is what I would say. We're working on it now. And really, we are doing the modeling and sim and the planning and all that now for really pioneering this new frontier. And it really is a new frontier, right? And what really goes back to your first question, Deborah, is you said, what is the altitude, right? The disagreement between 250, 450, 300. And I think that actually really, really captures it. We'll know once we go up in testing, and it's going to be about the mission, right? At the end of the day, it'll be the mission capabilities that it enables for folks on the ground, right? Whether it be the Joint Force on the DoD side, or whether it be up scientists with NASA or NOAA.
Yeah, I think I'll add that there are companies today that are pursuing VLEO from a commercial standpoint, and I know those launches are coming up in the next year. So it's more of an evolution of how we operate in VLEO. I think there's going to be, in the next couple of years, commercial demonstrations in maybe the higher altitudes, in the 300 to 400 altitude range. But as we learn more about the regime, the operations in VLEO will probably change. We'll start to find new ways of operating lower altitudes, potentially pursuing air breathing and so on. And so I think over the next few years, there's going to be a learning curve and also a growth in how we operate in that regime. But it's certainly a lot nearer than I think we realized.
I think we've flown, we as a species have flown a few things, in pretty low altitudes, and we've learned a lot through those. I think the next few years we're going to learn a lot more. We're really starting to focus on the regime and try to understand more, about the regime, and that the product of that learning is going to be enabling for some of these larger constellations that might, want to come and operate for commercial services of different flavors in the regime. But I don't think we've accomplished all the learning we need to accomplish quite yet.
Yeah, so here today we have the Aerospace Corporation has developed a satellite called DISC-SAT. I think some of you may have seen it. I think there's a few talks on it this week and a demonstration tomorrow around the same time. But so the technology is being developed actively by several different organizations, and so Aerospace has developed this DISC-SAT, which is flat meter type spacecraft that they plan to fly here in the next couple of years. You can imagine the shape of a disc would have certain advantageous aerodynamic properties for maneuver. I think we plan to demonstrate some of that. It also has interesting applications from a deployment perspective. Right now we deal with cubes, and cubes have been the standard for the small sat community. Flying discs enable you to to stack, store, deploy satellites in a very efficient fashion. So yeah, the technology's here. It will continue to develop, and it'll be really exciting to see how it goes.
And Deborah, if I can, I know we're thinking, a lot of times we think U.S. Centric, but I do want to give a shout out to the Belgians and ESA for their work and doing a Pathfinder on this as well. You know, our NATO allies and our partners are so critical in this adventure because we're going to learn from them. They're going to do the scientific exploitation, and then learning what we learn from the Belgians and ESA and what we learn on the U.S. side is going to really advance this for everybody and really the world, right? And so we want to, I would love to see more of that, right? More of our allies want to work together in this regime.
So we've talked quite a bit about some national security applications of VLEO. What about commercial and civil? Dean, you touched on NOAA. What would the National Atmospheric and Oceanic Administration want to do here?
Absolutely. It's quite possible to augment the current constellations. I think looking at weather augmentation, you know, look at the hurricane, and really we pray for the folks that were in harm's way today on the East Coast because of the hurricane, and the ability to maybe have VLEO satellite augmenting that to actually save lives, right, where there's flooding and other really catastrophic damage. You go back to Katrina, if we could have had VLEO satellites providing more persistence on the weather side, we could have saved lives, you know, in New Orleans and that area. So I can see a lot on the weather side of the house and really helping other folks that we have there. I think scientific is wise, learning more about, you know, not only on the environmental side, there's a lot to learn from the ozone to radiation to atomic oxygen and those things. And I think if you look, you know, when we decided to go to explore new frontiers, space, the moon, we learned so much on that journey. And we capture so much on that journey that really helps people and lives back home, right? If we had not ever gone to the moon, we wouldn't have Velcro today, right? And we wouldn't have some of the advanced communication technologies we have today. And so I think we're going to see same things. I'm not sure what it's going to look like. We'll all learn. But I think we're going to see some of these amazing capabilities that help everyday Americans, right? And that's really what we want to see for mankind.
Did you have anything to add, Jason?
Well, I think Dean covered quite a bit of it, but there's, you know, as we've talked about before, there's quite a bit that's still unknown in that orbital regime. It's actually a really interesting area where space weather has a lot of effect on the atmospheric density and in you know, interactions with signals. And so I think you know, the ability for us to better characterize the composition in those altitudes as well as the space weather environment will impact our ability to generate good weather forecasting, you know, communications that sometimes, you know, are affected by space weather events. And so the more knowledge that we build in that regime, the more that we'll be able to affect you know, some of our civil and commercial opportunities.
You have a bunch of space people here, and so we're excited about the space view of the world. I think there's a lot to be learned from as we bridge the gap between the air missions that we fly and the space missions. I think there's a lot of interesting overlap that we're going to be exploring, and it may open up entirely new missions that we have not conceived of today. And so I think there's a lot of promise in what we can do in this new regime. We have a lot of learning to do to be able to enable this regime to be used for new missions.
Not a whole lot to add to that, but if we can figure out how to build electro-optical systems with infrared capabilities, that obviously buys you a lot in terms of missile defense. But I don't like wildfires. It really messes with my ability to breathe. But you see wildfires pretty much all the time, especially in the summer during hot part of the year. And if we can figure out how to detect those faster, by exploiting VLEO, being closer to the ground, being able to sense better, I think that would be a good thing.
Yeah, I mean, Jeff, to that point, for folks who've been in Colorado, Canada, right? I was just there in Colorado within the last week and a half. The fire and the smoke, right? You could be in Colorado Springs, you could even see the mountain range. So being able to detect that and help our firefighters and first responders save lives and actually, try to put things like wildfires out is really critical, and it's actually impacts everybody's lives, right?
When I was talking earlier with my fellow panelists, we were talking about whether small sat would have a special track someday on this. It strikes me as this is a completely different conference. This is blending air and space and the strange space in between where what's possible there we are still figuring out.
Yeah, I actually think that's an interesting proposition, Deborah, because if you think about it, go back to where we said, hey, we're going to have autonomous airplanes or drones fly, within the pilot community. So you actually have a mix, and we do call SaferSat or orbital drone because it's very similar, right? Operating in this area between where air ends and space below LEO. And when you look at it, you'll have these orbital drones or satellites flying, right? With drones and then aircraft. And it's a really interesting mix of really, when you look on the DoD side, joint all-domain command and control, it's a mix of all of these, including LEO and GEO and MEO as well, working together, right?
I think that's an interesting thought. I think that it's a little telling that a lot of the work of the people in this room and the small sat community writ large has led to our ability, like, okay, I think we can actually go explore this regime now because of the efforts of this community. So, who would have thought, 10 years ago that the small sat community would be, looking at, trying to develop new missions for VLEO.
To that point, Seth, did you think 10 years ago you would see thousands of small satellites in LEO? No, right?
Although you might have thought that in 1998. I did. And I don't know if these will be small. Right? VLEO is so taxing, perhaps. You might need to be pretty capable and robust.
Yeah, absolutely. Just like any other satellite, if you're a GEO, the mission and the swap and the power and all the components you need really drive the satellite size, right? When you're going from SBUT, S-Borgandi, it's the mission that drives that. So I believe the mission capabilities for any operational programs will drive the size, right? How long it is, how wide it is, based on the variety of needs, right? To be able to perform that mission. Because at the end of the day, the satellite is providing a mission, right? It's from space, we're supporting, and on the DoD side, we're supporting the soldiers, the sailors, the airmen, the Marines, the Guardians on the ground. But, we're performing a mission from space. No different than the air side of the house. The air side of the house, the pilots are flying, but they're supporting, the folks on the ground, the soldiers and sailors. So I think it's the same kind of parallel, and the mission will drive the size, if it's small, medium, or needs to be large.
I think the question you had earlier, Deborah, was actually really good about whether VLEO is kind of unique to small sats, or this conversation coming up here. And I think to both Dean's point and Seth's, the work of this community, of this industry, to miniaturize and provide better capabilities in smaller swap packages really enables and opens up the design space so that it's based on the mission capability that's needed, rather than the limitations of the subsystems and the technologies. So I think this community actually has helped open up the VLEO capability area.
I think that the mission is going to drive what you need to build. I think that the VLEO environment might result in different looking spacecraft, because maybe drag is your dominant problem, and that's a cross-section thing, not a volume thing. And so, which might mean that VLEO is really great for some applications and really not great for others. So, but we're going to learn these things and figure out some of those scaling rules as we explore this environment.
Circling back to your original question, you see, I think this week we have a small handful of VLEO discussions. I think within the next couple of years, you could probably see a whole track talking about VLEO, and eventually perhaps a VLEO conference, hopefully hosted by SDL and Utah State, perhaps here in Logan.
I understand there's an opening next year around this time.
And will there be ice cream? So you've answered my questions, but what else did any of you want to say, or what are you thinking about VLEO that we haven't discussed?
I just want to talk about the partnerships to get there, right? I'll just say in a broad scope with Phase 4, we actually have a cooperation on a thruster called Valkyrie, if you're not familiar with our electric thruster partnership. And I think those partnerships matter across the industry, right? Where we're both rolling up our sleeves, working side by side for our customers. And I think I look broadly, I see so many friends and partners and people that we're supplying to, or that are working with us to build subcomponents or systems. And I think that spirit is really what's going to allow any space platform to work, but really on the VLEO side, I look at the partnerships. And then the second aspect I look at is our internal workforce, right? I'm so excited for our engineers who are just like kids in a candy store, right? They're excited, to go start working on this and produce amazing capability.
Yeah, I'll echo the sentiments there. The partnerships, between Phase 4 and Redwire, very exciting, and we're looking forward to developing technologies that open up, new regimes as well as supporting, current missions. One of the things that really supports this VLEO environment is the partnerships and the collaborations within this community. We've talked a lot, over this panel about developing new concepts and learning about the environments, and so I think the more this community comes together and develops use cases and new capabilities, new technologies that unlock it, I think it's just starting to really see the possibilities of VLEO.
I think the partnerships are very interesting. We're the government partnerships. I think the government industry partnerships. How can we exploit some of the unique facilities we have in within the U.S. government? I think that's pretty exciting. I'm still really excited about the new understanding of the regime that we're going to be hopefully unlocking for the community. There's so much that we don't know. We know a lot of things that need to be figured out. I think as we go, we're going to learn the unknown unknowns of things that we don't know today. And we're like, oh gosh, we didn't think about the autonomy is I think a pretty easy one. Like, okay, you need to figure out how to reboot your spacecraft fast and get your propulsion system turned on pretty quickly. That's pretty exciting. I think there's a lot more that we don't understand yet that we're going to be learning, and that's what gets me about it every day.
SmallSat has flourished under the academic environment. So many universities getting involved here. We have the student competition. I'd like to see universities start to offer courses and tracks in VLEO technology. There's a lot of great technology out there to be solved, and hopefully we can see that start to flourish in our schools.
Jeff, you just reminded me, I'll do a shameless plug. Regardless if you're a student or professional, if you're hearing this conversation and you're interested about VLEO and you want to kind of join the team, check out our HR team. Shameless plug, I didn't say that. I'll even say if you're an industry or government partner and you want to talk more about it, please come see me, come see Juan, and we definitely would love to talk to you about it. It's exciting, it's going to be a fun journey, right? And the most important thing is if you don't go to work every day and you don't have fun and you don't enjoy what you're doing, man, you should come to Redwire because we love it.
So we have a few more minutes. Does anybody in the audience have questions?
Quick hands.
Hi, I'm Mark from Singapore. I'm part of a national consortium which is building a very low orbit satellite that's going to fly next year. So my question really is, much has been said about the advantages of the very low orbit environment, what it can bring about for applications accordingly. Now, I'd really like to understand, from the operational standpoint, what are the disadvantages and drawbacks at very low orbit? So for example, we're looking at lower swath for Earth observation satellites using optical cameras. For example, if you're looking at fighting aero stability, how does this impact, let's just say, operational doctrine when we're sending up these kind of VLEO satellites for operation? Thank you.
I'll take the very first step. You know, operational doctrine is really important. You got to have your tactics, your techniques, your procedures. I'm a huge fan of that. But we're on this journey where we're not there yet, right? We're going to be building that, right? And learning. This is more of a new frontier where we're going to be learning things. And you're going to learn things what you need to keep doing, and you're going to learn some things, hey, we shouldn't do that maybe next time. And so I'd say we will get there eventually. I do see, in my view, I do believe there'll be operational capabilities where you have that doctrine that's going to be so critical. And that's a great question, by the way. Thank you.
Yeah, so, thanks, Dave Stephanie, Northrop Grumman. I'm just trying to line up the physics here a little bit. You talked about a range of altitudes and how that helps launch, but I point out the launch W changes by a couple % over that whole altitude range. You talked about 325, and then you talked about continuum flow and lift and maneuvering. The sketch up there looks like it's designed for a twilight sun synchronous orbit. And you know, the molecules you can collect go as velocity, I think, and drag goes as velocity squared, and heat goes as velocity cubed. So what are we really doing, and how are we doing it?
All right, I'll throw the first kickstart off. I think that same, by the way, great question, and don't take my answer in a really bad way, but I can go back, like I said, we're standing on the shoulders of the test pilots. I'm sure somebody said, oh, we're going to go Mach 1 or Mach 2, and we're going to go this altitude for this time frame. And people probably thought they were nuts. They're like, there's no way you can do it. You know, the engines won't work, the wings won't hold up structurally, and all that things, and we learned on that path. What I'll say there is we're on a journey, right? We're in this new frontier, and we'll know what we get to is we're gonna do testing, and we're gonna evaluate the specifics. The biggest thing I would say is this most important is the things we're gonna learn on the way, the scientific things we're gonna learn. You talked about on the propulsion side, we talked about some on the material side. We're going to learn a lot of things, and that will also just make us better, I think. But that's my answer. Jason?
Yeah, I mean, you touched on a lot of the physics challenges of the regime, and as Dean mentioned, there's a lot to learn there. I touched on this a little bit earlier, but you know, it is a feedback loop, and so you do have to thread a needle on a lot of those challenges that you just said. But I think they're problems that can be solved, and definitely worth exploring and continuing to develop in order to thread that needle.
Now that we've seen high-resolution video of this regime from Elon's latest re-entry, have you yet envisioned something like a smaller than Dream Chaser stainless steel-bodied aircraft with some of his heat tiles, or maybe competitive heat tiles and technology from the rest of the community made in quantity?
I do believe that we could see the value, and we can talk about the resilience value of a persistence or proliferated capability when you said numbers of them. I definitely think you could see value, the persistence it offers you, right? Persistence gives you coverage, it gives you the ability to have less data latency, it gives you the ability to have maybe better, if you're doing an ISR mission, ISR coverage, and if you're supporting national security, it's down to the warfighter. If you're supporting maybe NASA or civil, it's down to maybe first responders. So I definitely think you could see persistence. What that exactly looks like, we're not sure today, but I think it's a great concept. I mean, if you go back and look, I'm sure when, since you brought up SpaceX, when they mentioned Starlink and they were going to have thousands of satellites, a lot of people thought there's no way, right? How many people probably thought there's no way? And really hats off to them being a pathfinder on the proliferated LEO side, that they've done a tremendous job really for industry as a whole.
I'll just say that I love the idea of reusability. I know we approach this from a traditional orbiting perspective in terms of satellite design, but we've talked about before that these satellites are going to look very different in operating in VLEO, and so reusability and the concepts that might be able to be developed around that is very, very intriguing. So we'll find out.
Hey, everyone. As Seth knows, I'm a pretty big fan of the stratospheric layer, and as you guys were talking about the pros and cons of VLEO, I was listening. Wow, it's the same as, I don't use the B word, but you know what I'm talking about. From a cost and benefit, technical schedule, and the challenges, if you had like $11, would you invest it in stratospheric layer, doing these exact same missions, or the VLEO layer, and why?
I'll take credit for that. You're talking about balloons, right?
Thank you.
I've always been a fan of balloons too. They're cheap. You can proliferate and all that kind of stuff. But since you're solo, and VLEO has this problem too because your footprint is a lot smaller. You need more spacecraft. To get that coverage and that revisit rate, persistence, etc. For balloons, that's even worse. And balloons are controlled by the wind and all that kind of thing. And so I think from a mission management perspective and reliability and I guess mission assurance, it may be a little bit harder to employ balloons in a concept like that, although I certainly love the idea, and I think they certainly have their applications. So
I'll pick up a little bit. I think that while our understanding of the stratosphere and how to operate balloons is better than our understanding of VLEO and how to operate in VLEO, I still think we have a fair amount of learning on how we might operate, a large constellation of balloons to go after things. I think it's only in the last, I don't know, 5 years maybe that we've really gotten good at driving balloons where we want to go. I think we still have some work to do in that area in times 10 in VLEO.
I'm going to put Jeff and Seth on the spot a little bit. We talked a little bit about the art of the possible when we talked about various mission sets, and there are a lot of really good points that were made. But obviously, since you both have been on the other side or are on the other side, you understand demand signals are important. Are you understanding what the technical requirements or what the enterprise requirements are and starting to articulate that? Because you know as well as I do that that's very important, sitting on this side now of, hey, this is what we need and this is where we want to go for future missions and future technologies.
Thank you, Dan. No.
you're already talking requirements. You're killing me.
It's your fault.
So I'll open it up and back up just a little bit. Dean knows that I have lots of soapboxes, but I promise that it's only, this one will be a little bit softer. So actually backing up to the question from the gentleman from Northrop Grumman, when we talk about some of the challenges environmentally, specifically on the thermal side, and I've heard both Dean and Jason talk about innovations in specific component areas, so be it ballistic design or propulsion systems, but are you also looking at the factors that could actually influence going back to basic principles in the design of other components and other subsystems, for example, sensor subsystems, the microelectronics that go into it, and the way that those sets are fundamentally built, designed, and fabricated as a way to account for some of the challenges for this portion of the regime?
Great question, Jason. And I will tell you, when we look at modeling and SIM, we have something that we call our digital ecosystem mission and system integration, or DIMSI. And we're really using that, the digital side, to inform some of those trades and what it looks like. I'm really excited. We have a phenomenal team that are really leading what we call DIMSI, this digital engineering mission and system integration. And by doing that, we're going to look at components. We're going to be looking at a lot of the other the needs like C2 systems and things like that, as well as onboard autonomy. And I think that's going to really inform not only the first kind of iteration, working across both what we have now, but also SaberSat in the future.
Yeah, I don't know if I've got anything to add to that one.
We've hit on it several times that this isn't, every design is an integrated design. Any good systems engineer will tell you need to look at the whole picture. This is an integrated design and with different constraints and different advantages. And so it's our systems engineers who've grown up building things for the regular space environment now have some new things to think about and how they might design and integrate things for this environment.
Yeah, I think that's a great question. I mean, when you fly in space, LEO through GEO and beyond, you don't have to worry about things like aerodynamic forces or drag. So designing sensors that can conform to a spacecraft that's designed in a totally different fashion is a new area that I think Seth needs to explore.
Thank you for the great discussions. I think the space weather is one of the biggest challenge in VLEO regions. A big solar flare causes a great increase in air drag 10 times or more. So usually the constellation increase the resiliency of the satellite system, but in this case, it isn't effective because one solar flare damages all of the satellites constellations like Starlink. So what do you think about the countermeasurement toward a big solar flare? It doesn't cause frequently, but it may cause next years.
Yeah, I think that's a really important and challenging area for VLEO is the dynamic environment that you may not experience in other orbits. And so I think it puts a lot of emphasis on the unique design for VLEO, that you have to be able to react very quickly to changing densities due to space weather events. And so that puts emphasis on higher performance propulsion, as well as Dean's mentioned autonomy a lot. I mean, you don't have the time to have a human in the loop to react to those things in order to maintain your orbit. And that's something, to your question, that other constellations have unfortunately experienced the bad end or the downside of orbiting low, like Starlink, has lost a few launches, and so really requires very reactive, very dynamic space vehicles.
I think this will be our last question.
Hi, this may be a question for Seth and Jeff. There's been a lot of talk today. We have a lot to learn. But I was curious, is there any intention to share what you learned with the broader industry, so you can get more contributors to support and accelerate the adoption of this regime?
So yes, we'll be sharing the results that we learned with at a minimum the U.S. industry base, and so those will be coming. And as I mentioned, we have someone that we talked about the modeling of the environment and the interaction with and how the sun drives. This is the sun driving how the atmosphere behaves is going to be a much more important factor in this regime than it is even at ISS altitude.
And I think, like I said earlier, if we can start getting this technology into the universities, kind of like small satellites have been for the last 30 years, I think you're going to see a lot of that, technology emerge from communities like we're in right now. So, I can't speak much for the government side and how much they can share, but certainly there's a huge opportunity here for the academic community to research this area and share that information.
And speaking of shameless plugs, you can also always look to Space News to be covering this. Thank you all for coming. We've come to the end of the hour. Thank you to my panelists for an interesting discussion and to the audience for great questions.